Hello and welcome to this new and a quick tutorial on beam modeling. My name is Fadhel Al-Safar and we'll be talking about 1D versus 3D beam modeling and compare their solutions to the exact solution. And let's begin. Here's our problem today, in which we simply have a beam that's fixed from one side and have a distributed load on top of it, in which that beam is described by the Euler-Bernoulli beam equation as shown here. The boundary conditions, as I said, it's fixed on the left, in which the displacement and the slope on the left are zeros. And these will be enforced here. And on the right-hand side, it's free boundary conditions, which means that the moment and the shear are zeros. The material we'll be using is an isotropic material. We'll be using basically aluminum with these properties. And these are the assumptions that we kind of making during this analysis. We will be comparing our solution or the deformation along Y or the deflection with the solution, with the exact solution, and there's strong form approximation of that exact solution, which basically they kind of match exactly. And I plotted the results here. And what we expect to have, and these are the results that we obtained here out of the analysis, in which at the end of the beam, we're supposed to have a deflection here. Since I'm assuming a length that's equal to 10 inches, we're supposed to have a 0.15 deflection. So we run our analysis on both 1D and the 3D beam and 3D and compare our results. So let's start with Abaqus now. All right, here's Abaqus, and we'll start as usual with setting our directory here. All right, I have a shortcut here. We'll save it here. Okay, we'll change the model name here, and we'll start with the 3D model, since it's easier to visualize. So beam 3D. Now let's call it beam bending 3D. Most probably, if you start with a number here, it will give you kind of error and it doesn't accept that naming. So it's good not to start with a number here. So that's what we have, beam bending. And now we can start with making the parts. So let's call it beam 3D. So we'll be using 3D deformable solid, and the size, since our length is 15, so I can choose like something around that. So let me put 20 here, and it's a triangle, and its first corner is a rectangle, and its first corner is 0, 0, and the second corner is at 15, and here we have the width as 1, so that's 15 and 1, and that's what we have. And done. And now it's since we're extruding that, and my thickness again is 1, so that's what we have here. And now we move to property, and as we said, it's aluminum. And its mechanical property here, elastic. The Young's modulus is 10e6 with Poisson's ratio of 0.3. And okay, we need to create a section here. Let's call it here beam section. And we are doing solid, homogeneous. We're not doing any composites here. So let's create this one here. It's right. And since now it's a green, we're good to go, and the material is assigned to this beam here. Now we need to go to assembly. In assembly, we need to create an instance first. And here I prefer to use independent, in which we're creating an instance and we are meshing that instance. Okay, we're done with this step. Right. So let's call it load step, and it's static general. Okay. And here we can keep this as they are, or if we want, if we want to see the deformation in quite multiple steps, can have this one as 0.1, and this one has a maximum step of, let's say, 0.5. Okay, and now we need to go to loads, and let's start with boundary conditions. If we go back to this example, we have boundary conditions that are fixed, which means that all X, Y, and Z and rotations are fixed. And Abaqus, we do have this boundary conditions. So we have this, let's first start with the naming, fixed boundary conditions. And if you go to the first option here, you have symmetry, anti-symmetry, and this last option, which is for the fixed boundary condition. If you click, and if you rotate this here, and choose face, choose this face here, choose this option, and it's fixed now. And I just realized that I made a mistake in which the length is supposed to be 10, not 15. So that's a good opportunity now to go back and see if you want to edit how to do it. So you can go back here, parts, beam, and then go to features here. And then you can see here, you have the sketch. If you double click on this, you can see here, now you can see that the sketch that you did. And we can go to dimensions here, add dimension, and we can see this is the 15 that I chose, and I want to make it 10. So that's 10. So now it's shorter now. That's good. Let's click done. And here it just says that you need to regenerate it. So that's fine. Let's click OK now. And the way to do it is to right-click here. Nope, it's not here. Possibly somewhere here. Let's try to find it. Solid. So yes, we need to regenerate that, and the way to do it is to go to features here, right-click, and just click regenerate. And now you can see now the beam is shorter. Cool. So now we can see it here, and we can proceed where we stopped. Let's see it 3D. The last thing that we did is we applied the the boundary condition, and we need to apply the load. Now to apply the load, we'll do something that's quite different than what we did last time. So we'll create the mesh first, and then we create a surface on that mesh, and we'll go back to apply the loads on these nodes that we meshed. So it's good. So since it's a green here, it means that the structure, the mesh will be structured mesh and hexagonal. So that's good. So the size, since I have it in inches, so I'll choose a value of 0.1, for example, so that it's well meshed, and I'll mesh it. I need to assign element type. So, and since here what we want to do we're applying the load, and there will be a bending moment, and there will be a generated shear on that on the pipe. The regular element may introduce a shear, what's called a shear locking phenomena, and which occurs due to kind of limitations of the element. So we can use an upgraded element in which it will take into account the effect of shear, and we'll calculate that. And the way to choose that element is when I went to element type 3D, you have this option here, incompatible modes. And when you click on this, you can see that now you have this element here in which its name is C3D8I, which is an element that takes into account the shear locking. If you want to know more about it, you can Google it, and you go to you Google it and see information about that. So actually, if you Google this, and let me do it here, and so that you can see here, you can see that there's the element, and this is incompatible mode element, in which it has 8 nodes, and it says that here shear locking is removed and volumetric locking is much reduced. So that's kind of the function of this element, and you can read more about it as well. And there are other options here that are mentioned as well. So let's go back here. So we chose our element, and as I said, we'll create the mesh, and then you want to select a surface, and then that surface will be using it to apply the loads. So to do so, we'll go here to tools. Just a second. In tools here, we should go to surface. We can go to manager and create here, and let's call it here loads surface, and continue. And the way to do it, we can click on this one here and say done. Now we created that surface. We can go back to the load now and create here a load and select attraction load. We have surface attraction, this one here, and let's call it distributed load, and click OK here, and you can see here, if you go to surface here, you can actually select what we created before, which is this one. Okay. And here in this window, it asks you what type of force that you want to apply. So it can be shear or something that's general. And the general, you need to assign the dimensions to it. So you first choose shear. You choose general, and then here it says direction. You go to vector and you click here, and here it asks you to select the direction of that vector that you apply, that you want to choose. And we basically our force vector here is to point downward. So to do so, he's asking you to choose 2 points, in which the direction of that vector between 2 points would be the direction of the force. So this is our first point, and this is our second point. And now you can see here its direction is -1 in the y direction. And its magnitude here, if we go to our problem, we're applying 100 pound per inch. So that's kind per inch in length, and per inch, the second inch is within the width. So we're applying here a 100 basically. That's 100, and it should not follow the rotation. So you should unclick this one here. So you can see now we have the load. If we just do this, oops, it's not that clear. It's there. Yeah, it's there here, and it's applied. It's downward. So now we're done with the property assemblies there, and our step. Within our step, we can go and make sure of our output here. So let's go here and let's select our parameters. Basically, what we want here, we want to, at least for this problem, we just want to compare displacement. So I'll unclick these here. No contact, not this. I just need the displacements. So yeah, that's you should be enough now. And I can I can create a point here, as I said, so that I can monitor what happens here and create a history output. So let me show you what I can do. Create. So I'll call it top point deflection. And let's click here. So I want to see, for example, this one here. And I created now a set or kind of a point. If I go to output, history, and manager, and create here, and let's call it top deflection. So now what I'm doing is kind of I'm creating a step, I mean a point in which I want to monitor the deflection of that point later, and it would be with respect to time. And the way to do it is by creating a set, which is that point that I did here, and then creating a history output. And again, I just want to get displacements and only U2, so on deflection along Y. So it's good just to choose only what you want, because selecting more things can take consume time during simulation, during solving, I mean. So now we believe we're done here, and we can one more thing is that we're done with this element. Yeah, so that's good. Let's go to job here, and let's create the job, and let's call it the same name, beam bending 3D, and continue. Okay, and then we can go to here. Let's run a data check. Let's hope that we didn't make any mistake here. You can go to monitor here. See if there's any warning message. So that's good. There's no warning, and the check is complete, and we can submit this here. So as it's processing, we can kind of reiterate what we want to do. So we want to model the beam in 3D, and then we'll do a 1D beam modeling, and we want to compare the results. One of the reasons for doing that is that 1D modeling reduce the computational time a lot, so that can save a lot of computational time. And if it can give us very, very close or similar results, then it will be wise to use it. And we want to compare their results to this result here. Okay, let us go to, okay, it's done. That's good. So let's go to deformation here. And as I said, we want to see the displacements, and we basically want to see U2 displacement, which is the deflection W. And if we take a look at this, and so let's try to see it more clearly here. And as you can see here, that the total displacement or deflection of that pipe, which can be seen here by this color bar, is negative 1.502, which is very close to the value that we obtained theoretically, which is 0.15. And if we want to see better, we can go to the points that we create as a history output. We can go to here, create XY, and then go to history output. We created a history output. And then here we have a few things that were created that we actually do not need, but what we want is the displacement. So if you look for it, you can see here, spatial displacement U2 at top point deflection, which is the point that I created. And if I say plot, you can see here the total deflection as a function of time here, but you can see how it looks like. If you want to see total deflection in terms of displacement, we can do that. So let's bring this back, and we can use our path function, in which we go to tools and then go to path, and let's call it deflection spatial. And let's take node list here and click continue, add after. And we're basically now we are selecting from the viewport, we're selecting the points that we want to select. So basically moving around the edge and selecting points. So you can select as many points as you want, but just to save time, I'll try to move fast. And you want to compare our plot to the plot we obtained theoretically and see. Oops, I can do undo here. Okay, good. I can zoom in as well. So let's do this. Zoom out, zoom in. Okay. And let's take the last point, the last 2 points here. So we selected that. Let's click done, and now okay. Now we saved it, but to see it, we need to go to XY data here, go to path, click here, and we want to do a plot. However, when we selected that point, the frame that we chose was that 0 frame, which is before deformation. We want to see the last frame, which is after the deformation occurred. And the way to do it here, go to step frame within this window here, and click last part, and just click this. And now click on plot. And you can see here how the plot looks like here. It looks very similar to the analytical plot that we had here. And it goes from 0, no deformation, and it goes here all the way to negative 0.15. If you want to output that data, you can do that. You can go to save as, select a name, for example here, deflection data 3D beam. Once you do that, you need to go to report XY, and then this is the data that you created. And if you want to save it, you need to go to setup, change the extensions. It's better to use CSV or TXT file and save it and choose a name. And then once you click OK, you will be able to see that file in your folder. So the first saving process that we did, that was saved within Abaqus, but if you want to save it in your folder, so kind of you output that file, this is the way to do it. So that's good. We modeled this by now using that an element that prevents shear locking, and we can see that the value is very close to the exact results. but we said we want to do 1D, and the way to do it is, let's go back to our model. Let's create model here. Let's right click here, create, and now let's call it beam. Let's have a name that's quite close to that one. So beam bending 1D. So we created our as a second model, and now we need to create a part. So beam bending, let's got 1D as well. Now we'll do 2D here, and within 2D we'll choose wire. So previously we chose 3D, now 2D, deformable wire, and the size we can leave it at 20. And now we basically will model that beam as just a line. So we'll go to here. The first point is 0, 0, and the second point is 10, 0. That's it, just a line. Done. And that's our part now. Let's go to properties, and it's aluminum. Same properties as the last one. We have 10, E6, 0.3 Poisson's ratio. Okay. And now when we do beam, the cross section is assigning it is a bit different. So to do it, we need to go here. If you go to the left, you can see an option which says create a profile. Click, and you can see here create a profile, and you can see here different options, and they're basically for the beam element. Now, you may probably use it for others, but you for sure they're one of their uses for beam elements. So let's call it here beam cross section, and our cross section is rectangular. So let's choose this one here, and let's click OK. And now it asks you to define the cross section of that beam, of the beam that you have. And since here the beam that we have has a cross section area of 1 by 1, on the previously we did it in 3D, but now we need to enter it here. So that's the cross section. And then after doing that, we need to go to, I believe, section manager, and then select this one here. Oops, no. We need to go to this point here, and let's call it again beam section solid, and now you need to select beam here. Yeah, that's kind of different. So you go to here to create section, beam section, select a beam here, and you select a beam here. And now when you click on this, you can see here, oops, the cross section that we created before within this step here is shown here. So that's what we created before. And you can see here it asks you about the material properties which we created. Poisson's ratio, and the Poisson ratio that we have here is 0.3, and we do not need to do anything else here. So let's click OK. And if you notice that it's not green yet, we cannot move until it's green. So let's make it green here. And the way to do it is to go to section assignment. We need to assign that section. We created the section. We need to assign it now. So done. And okay, now it's green, so we can go. Assembly, we create assembly here. Game part independent. All right, and that's done here. We go to step. We create a step here. Let's call it load step. Again, it's general. So let's click here. And let's do just like what we did last time. Let's have this on 0.1 and this one is 0.5 so that we kind of see deformation. If you want to do to see simulation, let's go to output again. We only want to see the displacements for now. So only U is enough. So at least we do not need it for now. So only the translational displacement. So translational or rotational, we will get them both. If we want to do something similar to what we did with that one, which we see the deflection at the end, we can do that. We can go to here, create a set, and let's call it end deflection. And we can choose a point here and hit enter. And you can see here, the point is created. To see it later after the simulation, we need to create a history and create history output. Let's call it and deflection. And we want set this one, we want displacement, and we can select only this one here. And we're done. We need to go now to load. Let's apply our fixed boundary conditions. And just like what we did last time, which was the first one here, and let's select this point. And let's say that this point is fixed. So you can see that now it's fixed all degrees of freedom. You can do it manually when you go to displacements and fix them all, but this is one option that you can do it once. You can do them all at once. Now we need to create a load. For this load, we can do it now this way here directly. So let's call this reputed load. Now we can use line loads since it's 1D. And let's select this one here. And again, its value is 100 and 100 is pointing down. So that's negative 100. And yeah, we can see that it's pointing down and we're good. We can go to here to mesh. And within here, what we can do is let's choose our size here. So it's 10, so let's have 0.1, just like what we had last time. But now you can see that when we mesh it, since it's 1D, last time we had around 10,000 elements. Now all the elements that we have is only 100, and we're using kind of same resolution. So let's see how that will end up. If we go to element type, we are using beam element, and we're using B21, which is this element here, and we'll be trying different elements and see different results as well. But for now, we'll start with shear flexible here and linear, and with these options. Click OK, and now we mesh it because here now it's a line. You cannot see the mesh, but they're there here. We mesh. We're done with this one, so I believe we're good to go now. So let's create our job. And let's call it beam bending 1D. And we want this model here. Click OK. OK. And now let's submit it. And it shows us an error. And let's see what that is. Yeah, for when you do a beam, you have to assign the beam orientation. Let's go and figure out more about this one. So the way to do it is to go back to property and to go to here, assign beam orientation. And then choose this one, choose the beam and click done. And you can see here, it asks you enter the approximate in one direction tangent vectors are shown, in which it shows you the tangent vector here. And what that means basically is, let me click OK. And now that it shows you what that means, that shows you the tangent, which is this arrow here that says T, and other 1 and 2 dimensions. If you Google this and go to see what that is, you see the following here. You'll see this here. You Google it and you'll see that when you assign the orientation of the beam, it basically you assign the orientation, that's the tangent, which is along the length of the beam, and the N1 and N2 are the dimensions of the cross section that you assigned. So that's kind of how you make sure that when you assign the cross section for the beam, it's actually for match what you want and what you expect for your geometry. In our case, yes, so that's the length of our beam, and the cross section is going this way and that way, and that's N1, which is the A parameter that we inserted in the cross section, and N2 is the B parameter here. So that's the beam orientation. And now we did it, and let's click OK. And hopefully now we have everything done. Let's go again to job and let's submit it. Or this one's supposed to calculate the results in really quick, since we only have 100 elements and it's 1D. And it's done. Let's go to results. And let's go to information. Let's see our beam. Let's move this to here. And this one to here. Yeah, this is a lot better. So that's our beam, and we want to see U2. And if you look here, the value that we have is 0.1515. So that's very close. So if you go back and see our exact solution, it's 0.15. So it's 0.15, and our result is 0.1515. So the error is 0.0015 or so, or the error is quite small. I haven't calculated the values now, but you can do that. So that's good. If you want to see the beam, with its cross section or so, it's quite hard to see. There is kind of a trick that you can do here. If you go to view and you go to ODB display options, you click on that, and you'll see an option here that says render beam profile. If you click on that and you click apply, you can see that now it gives a kind of cross section of the beam, and you can see it if you want it. That's more appealing for the for seeing it and for presentation. So if you want to do this, you can do that. But now let's see that our results, though that it's very close, and with only 100 elements, we can actually do it better. And the way to do it is to go back to our elements and choose one that counts more for the shear, so that has more nodes. Let's go back to our mesh within this 1D, formulation, and we go to assign element type, and within here let's select cubic formulation here. Within cubic formulation, you can see here it says that it's to denote the cubic beam in a plane. So now this one has uh, it uses a cubic equation to calculate the the cubic equation for the shape element used in that in the beam. So let's go to job and submit it again and see. And it's done, I think. Yeah, it's done. Let's go to results. Let's go to deformation. Let's go to YouTube and look at this. Now it's got the deformation. It got almost it got the exact solution here. So that's awesome. Now we used 1D elements and we got the exact solution now. So in a relatively shorter time with less complexity. And if we want to plot data, we can do just like what we did last time. We can go to profile, see our history data, or create a path and see the data along this one and output the data. And with this, I kind of end my presentation and what I wanted to share for this one here. So again, what we did is we modeled this beam here with these input parameters, and the problem we solved is that for Euler-Bernoulli beam with distributed load, we did it with 3D elements, and in the 3D element we used that the element C3D8I, in which it takes into account the shear and prevents what's called shear locking. And then we moved to use 1D, and within 1D we used the linear element, and then we used the cubic element, and we saw that within the cubic element how we got the exact solution. And you can as well see within that 1D formulation, you can actually get the exact solution even if you're using the student version of Abaqus, because all numbers that we needed was 100 elements. So with that, I end my presentation and hope it was useful and enjoyable. So thank you.